Conduct today's class. So I welcome all of you to the class. As far as the today's class is concerned, in today's class we'll be solving few numerical problems based on the concepts which we have discussed previously. Okay, so let me take a very simple problem today. As far as today's problem is concerned, today we are going to solve the problems for finding the stresses and strains, okay, in the machine elements. For example, the question here is we are given a machine element. The machine element exists in the form of a rod. Okay, we have a machine element and the machine element is in the form of a rod. Okay, the machine element is having some area of cross section. Let's say its area of cross section is, say, for example, A. Okay, now this machine element is being subject to loads. Okay, and it's having load of 5 kilonewton about along negative x-axis at point A. It's having a load of 8 kilonewton at point B. It's having a load of 4 kilonewton at point C, and it's having a load of 7 kilonewton about negative x-axis at point D. Fine. Now the question says, what is the total stress in the rod? Calculate the total stress in the rod as well as calculate the total strain in the rod. So we have two things to solve. We have to calculate the total stress of the rod as well as we have to calculate the total strain in the rod. Now, as far as the stress is concerned, look, if we have a machine element that exists in the form of a rod, and we know if this machine element is subjected to load P and its length is, say, for example, L, its length is, say, for example, L, its area of cross section is, say, for example, A. Okay, then we define the normal stress in this machine element is equal P by A. Okay, and we define stress is equal Young's modulus times the strain, that is change in length divided by the original length, and we know the value of stress is equal to P by A. Fine. This is this procedure we use, these formulas we use when we have the machine element subjected to forces at only at its two ends. But look at the problem here. This problem is quite different from this problem. Okay, in this problem, apart from loads at the free ends, there are loads at the in between the points. Okay, in the between points, in the mid points. Okay, in the points that lie between A and B, at those points we are having the loads acting. So whenever we have a problem of this nature, what we do, we take the sections. We take the sections. So what do we mean by taking the sections? By saying we take the sections is what we have to do. This entire problem you have to divide into small problems such that each or this entire element, this entire structure is to be divided into small elements, is to be divided into small elements such that each element will have the shape will be fundamentally like this element of some length and area of cross section and is being loaded at its two ends only. This is how we have to solve this. We have to reduce this problem. So what we do, we first of all draw a section here, AB. Isolate this AB. Okay. So as we isolate the section AB, so we have AB section like this. We have this is section, this is end A and this is end B. Okay, the length of this element from A to B is LAB. Fine. At this end, this element is subjected to a tensile load of 5 kilonewton. This is 5 kilonewton here. And at this end, it is subjected to some load. Now look at this end. At this end, we are having only one load, that is 5 kilonewton. But at this end, okay, this end, on this end, okay, this machine element is subjected to a load of 8 kilonewton as well as a load of 4 kilonewton as well as a load of 7 kilonewton. Okay, so at this very end we'll be taking the resultant of all these loads. So we treat loads acting along positive x-axis as positive and loads acting along negative x-axis as negative. Fine. So on this end, we are having a load of 8 kilonewton plus a load of 4 kilonewton and a load of minus 7 kilonewton. So total will be 5 kilonewton. Okay, and this 5 kilonewton is positive. It means it will also be acting along positive x-axis. So here we will say it is subjected to a load of 5 kilonewton. Fine. Apply the formula as far as the stress is concerned. So we'll write stress on the rod AB is equal to force, that is 5 kilonewton, divided by the area of the rod AB, that is A. Okay, therefore we know stress in rod AB is equal to Young's modulus of times the strain in the rod AB, that is 5 kilonewton divided by area is equal to Young's modulus of times the strain, that is change in length delta L of the portion AB divided by length of portion AB. Okay, therefore therefore we can write the change in length delta L in the section AB. I will write it like this: change in length of the section or element AB is equal 5 kilonewton divided by area, 5 kilonewton divided by area, and multiplied by length of the section AB divided by the Young's modulus of elasticity. Fine. This is how we calculated the change in length of the section AB. So this I will call this gives us, or this gives us the stress produced in the section AB. I will call this as equation 1. And this gives us the change in length of the section AB. I will call this as equation 2. Okay, let's go ahead. Now let's talk about the next section. The next section is the section BC. Fine. So as we talk about the section BC, isolate the section BC. So this is B, one section is here, another section we draw here. So when we talk about the section at point B, on this very side, we will be having two loads. We are having a load of 5 kilonewton acting along negative x-axis and a load of 8 kilonewton acting along positive x-axis. So the total load acting on the section B will be minus 5 kilonewton. This is minus plus 8 kilonewton. 8 minus 5 is 3, so it is 3 kilonewton. Since this is positive, it means it will be acting along positive x-axis. So we can write it here. I will write it here for section BC. For section BC at end B, we will be having a load of how many? 3 kilonewton acting. Fine. So this is 3 kilonewton. Now look at end C. At end C, you are having 4 kilonewton. This is positive. 7 kilonewton is negative. This is minus. So this is minus 3. Minus 3 means it's acting along negative x-axis. So it's like this. Okay. So it is 3 kilonewton along negative x-axis. Again, use the formula. Therefore, stress in the section, this is C. Okay. Stress in the section BC is equal to force, that is 3 kilonewton divided by area. Okay, now again calculate the change in length using the previous formula, which I can directly write the change in length in the section BC is equal here we had 5 kilonewton by A, here it will be 3 kilonewton divided by A multiplied by this is here length of AB, so it will be length of BC divided by Young's modulus of elasticity. But look, since 3 kilonewton in the section BC will try to cause the compression in the rod, it will tend to decrease the length. I had already stated that this change in length is to be taken as negative. So we'll be writing here negative. Okay. Now we'll go to the last section. The last section that we have is the section CD. Now as we go to the section CD, as we go to the section CD, okay, so I will write this section CD. Let me here. By the way, I will call this as equation 3. Okay. or I can call this equation as equation 3, and I can call this equation as, can call this equation as the equation 4. Let me call this equation as equation 4. Fine. Now let's talk about the section CD. As we talk about the section CD, on the ND, we are having a compressive load acting of 7 kilonewton. Okay, so I will write this as 7 kilonewton. Now what's on the left hand side? Okay, so we are having 5 kilonewton minus plus 8 kilonewton plus, and this 4 kilonewton plus. Okay, so 8 plus 2, 4 is 12, 12 minus, this is 7, and this 7 happens to be positive. Positive means this 7 kilonewton is acting in this direction here at end C. Therefore, we can write stress in the section CD is equal to the load, that is 7 kilonewton, divided by the area, that is A. Okay, I will call this as equation 5. And we can directly write the change in length in the section CD is equal 7 kilonewton. Okay, 7 kilonewton, 7 kilonewton divided by the area. So this is 7 kilonewton divided by the area, 7 kilonewton divided by area, multiplied by the length of the section CD, length of the section CD divided by the Young's modulus of elasticity. Look at this 7 kilonewton load. It's also trying to compress the machine element, so this will also be taken as negative. Let's call this as equation 6. Therefore, the total change in length, look here, this change in length is positive. Okay, so the section AB will try to undergo the elongation. Section BC change in length is negative, it will try to undergo the reduction in the length. Same is the case for section CD, it will also tend to undergo the reduction in the length. Therefore, the total change in length, okay, the total change in length will be the corresponding sum. Therefore, we write the total change in length, or we write here the total change in the length, delta L, total change in length of the rod AD is equal change in length of the section AB plus change in length of the section BC plus change in length of the section CD. That's equal change in length of the section AB, that is 5 kilonewton divided by A, multiplied by length of section AB divided by Young's modulus. This is positive, okay? Then we have length of section BC, change in length of section BC, that is negative. So that will be 3 kilonewton, that is 3 by A, length of section BC, LBC divided by area. And about section CD, it's also negative. So we have to take it in minds because it's compressive as is given in the formula. So it will be minus, okay, 7 by A into length of section CD divided by the Young's modulus of elasticity. Okay, we can further modify this equation as, okay, this equation can further be modified as change in length, sorry, total change in length of section AD is equal, A is constant everywhere, this is area of cross section, okay, E is constant, okay, so we can take this 1 by AE out, okay, so what will be inside, it will be 5 times length of AB minus 3 times length of section BC minus 7 times length of section CD. This is the total change in, this is the total change in length. This is how these questions are to be solved. Now, if you go to some unsolved section, let me quickly go to the unsolved section of this RC Hibla. There are many questions that are based on this concept and which you should be able to solve now, like these questions. Okay, look into this fundamental problem. Let me annotate. You have a problem 4.1. This problem is to be solved. This problem is to be solved. Okay, in the same way you can try this problem. Okay, um, okay, that's fine. You can do these types of problems. I request my students that they should solve all the problems of this section. That is up to fundamental problem 4.5 you should be able to solve. Okay, because these problems are simply based on this concept. Students, look into the question. I'm sharing two questions with you on my screen. One question uh, I will be solving. Another question I'm leaving to you as an exercise. So you can take a snapshot of the screen to keep a record of the question. So as far as the question is concerned, look at the question one. Okay, the question one says determine the stress in each section of the bar shown in figure 1.19. This is our figure 1.19. In this figure we are given a question which is subjected to an axial tensile load of 20 kilonewton. The central section is 30 mm square cross section. The other portions are of circular cross section. Okay, their diameters being indicated. Fine. um, what will be the total extension of the bar? The same question as we have been doing. Now look into this question. We are having the loads are acting on the entire rod only at its free ends. But the problem now is that the rod area of cross section is not same everywhere. Okay, if I divide this rod into sections, I will call this as, this is section AB, this is section BC, this is section CD. Okay, area of section AB is different than the area of section BC, which is different than the area of section CD. Okay, so what we will do, we'll go ahead with the same procedure as we have been going in the previous question. Let me take section AB. Okay, for the section AB, this is A and this is B. So I'm having a load of 20 kilonewton acting. Okay, again for equilibrium purpose. Okay, this portion is in equilibrium with this portion. That is only possible when you will be having a load of 20 kilonewton acting on the section at BC. Okay, the load will be 20 kilonewton. Only then this portion will be at equilibrium. It will not be moving at all. Okay, now for the section AB, we have to find the total extension of the bar, total extension. So for the section AB, we'll write the change in length of the section AB is equal to, if you look at section AB, it's under tensile load, so the change in length will be positive. So it will be load, that is 20 kilonewton, that is 20 into 10 raised power 3 Newton, divided by the area of cross section. The area of cross section is given to us as the 20 mm square. So it is 20 mm. What will be the total the other portions are of circular, their diameters are indicated. We are not given this as an area, this is just the diameter. Okay, so we have to calculate the area. So the area will be pi by 4 d square, because this is of circular cross section. That will be pi by 4 d square, that is pi by 4 20 mm square. Okay, this is the change in length. Sorry, so this is p by a multiplied by the length of section AB. The length of section AB is 250 mm, because we know P by A is equal to Young's modulus times the change in length divided by the original length. Okay, so we can write PL divided by AE as the change in length. Okay, so this is P, this is A, this is L, this is 250 mm, divided by Young's modulus of elasticity is 200, and this is giganewton per meter square. That is 210 into 10 raised power 9 Newton per meter square. Okay, so what we will be doing, you have to convert this mm into meters. That I am leaving to you. This will be the change in length in the section AB. Now you'll be going to the section BC. Go to the section BC, change in length of the section BC, again using the same formula. If you look at the section BC, it's again an equilibrium. Okay, on one side it is subjected to a load of 20 kilonewton, and on other side it's subject to a load of 20 kilonewton. So total load acting on it is 20 kilonewton, that is 20 into 10 raised power 3 Newton, divided by area of cross section. It is of rectangular cross section. It is given us the center is a square cross section. Okay, it is given, and its each end is 30 mm. Okay, so its area will be 30 into 30 mm square. Okay, multiplied by the length. Length is given to us as 100 mm, divided by Young's modulus of elasticity, that is 210 into 10 raised power 9 Newton per meter square. Okay, this is for section BC. Similarly, talk about the section CD. As you look into the section CD, on one side you are having 20 kilonewton, and on the side you are having 20 kilonewton. So again, it has same. So it is 20 into 10 raised power 3 Newton, divided by area, that is pi by 4, it is circular cross section, into 15 mm square, multiplied by its length, that is 400 mm, divided by 210 into 10 raised power 9 Newton per meter square. Okay, so calculate all these delta AB, delta BC, delta ACD, add them up, you will get the total change in length. As far as the answer of this problem is concerned, let me see what the answer says. The total change in length for this section is, the total change in length for the entire rod is given to us as um, just a minute. The total change in length is given as 0.302 mm. So let me write the answer for this problem. The answer for this problem is, you can check, is 0.302 mm. Okay, solve this problem to obtain the direct answer of 0.302 mm, and solve this part A of another question, and part B. You will be solving only two parts of the next problem. Okay, part C I will be showing myself. So please solve this problem, and if you have any problem, you can refer back to me. Okay, any problem right now? Have you taken the screenshot of this problem?
Yes, sir.
Okay, please do this problem and complete the problem one. Do problem A, problem B, and refer back to me in the next class. Next class is on Saturday. Let's see what happens, whether we will be continuing with online class or not. It's your decision. So thank you very much. Let's meet next time.